Okay.
So today I'm going to introduce BigDL-LLM. It's a low-bit LLM library on Intel XPU. So before that, we send the when I send the abstract, we want to show how to deploy Llama2 on laptop. By that time, like Llama2 was still popular. Like now it's changing very fast. So I just want to, I hope you guys don't get disappointed, and I will introduce more stuff. Yeah, not just on Llama2 and on other stuff too. So here's what I'm going to cover today. First, I will go through some background of large language model. I'm pretty sure everybody heard about that, but just in case, if somebody has low background of large language model. Then after that, I will talk about BigDL-LLM library overview. So in here, I will go through a little bit depth into the details, how we develop this library. And after that, I will go through some demos and the usage, let you guys see how it looks like and how to use it. Then this tutorial, if you guys interested, we can host another session to do on GPU or CPU together. Then this is to be done. Yeah. How about that? Okay. So first, the background of large language model is, I guess a lot of people, especially in Silicon Valley, everybody was very much interested into large language model. Everybody was talking about that. Everybody, wants to get into it. As Dr. Hu said, maybe this is a next trend for AI to get hooked up. So just that means how popular it is, and it's getting everywhere, especially since last year, like a ChatGPT came out, and now Bard is over there for everybody to play. Then we want to see what is large language model. It's a part of generative AI. So what is a generative AI? It's a subset of machine learning. So what is machine learning? Machine learning is that you have some data and you do the static learning and get the pattern. Yeah. So if you have usually you put a prompt into a generative AI models, for example, you say, tell me a story in one sentence. This model might tell you, once upon a time, in a bustling city of whispers, the last blah, 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 it keep going. If you tell the model to say, hey, give me an image of tulips, it might give you a limited access one. So it's a machine learning model that generates stuff, generate content. Okay. So what is exactly large language model? What does the large language model generate? These large language models are designed for natural language generation. It's not for image, it's not for video, it's just for language generation. This is a video for GPT-3. Once you have these tokens and you go through this large language model, it's kind of a neural network. Stacked with transformer decoder layers, and then you can generate stuff. That's how it is. It's based on stats, depending on the first, second, and then the conditional probability you predict what's the probability of next word. Yeah. Does that make any sense to you guys? Okay. So what can large language model do? They have strong capabilities for understanding natural language and solving complex tasks, except like answering questions, generate other texts, translate languages, summarize texts, or like writing code, or any other, a lot of creative content. This is an example how it looks like. How does it work? For chat, looks like one. If you have a client, tells you, hi, the assistant might go through a large language model, tell you, how are you? Then you go through, hey, what is AI? It might give you back a question. AI is something. I'll give you an answer. Like AI is something. So it's like a generic chat bot. If we use this for conversing with large language model, but the backend, we use large language model, not by the search, not by other techniques. So it's the large language model on the backend is generating all this text for you. Yeah. Okay, we can tell like with the increase of parameters, the more parameters the large language model can handle, the more tasks it can solve. If you have a very small model, you probably can do this much. If you have a slightly bigger model, you can do a little more. Then the question is, do you think the large language model, do you think the parameters will go infinity? Obviously, it's not. There's some limit because there are some challenges going on. First, the large language models are really large. Because the parameters are so big, we need a lot of resource, and it's very costly for the hardware. You can just say this is a RTX GPU price. Given this much memory, you have to pay like more than around like 1,600 for this GPU. And the size, think about this, just 7B Llama, we have to have 14 gigabytes for FP16. If it's 70 billion parameters, the size goes to more than 100 gigabytes. So it's a mismatch. The model gets so big, but the memory is very small. Then what can we do? I will answer question in a little bit. Yeah. Another challenge for large language model recently is a lot of people want to deploy the large language models at local because the data privacy, and we are not very. I think it's on the news a lot. See, some companies says, "Hey, we want to ban stuff's use from after spotting like ChatGPT data leak." Where Apple joins this list of companies cracking down on the use of ChatGPT by staffers because of the privacy. Because a lot of these companies, of course, they should. I mean, they don't want their staff send their personal or company data to OpenAI. They want to make sure. Yeah. Then what can we do? If we don't send the data to OpenAI, you still want to use the large language model capabilities. Then they want to deploy the models at local, but they are so big and we might don't have that much resource. So what can we do? Luckily, for like companies like of course for Apple or Samsung or even other big companies, they have the capabilities to develop their own large language models. But how about for the medium-sized companies? Do they have that much like resource, including engineering resource, including the hardware resource, and how they compute this resource to develop, to train these big models? The answer is no, actually. For a lot of medium-sized companies, they don't have the capabilities to do that. Luckily, there's a open source community, the Hugging Face. It's a platform that machine learning community collaborates on models, data sets, and applications way before like large language models came out, like BERT. Even before BERT, there are other models are open sourced on Hugging Face because people trained on like standard data, trained on the big models, very good models, and put it on there. Then other people can just use it. So this transformer API, it's a Python library released by Hugging Face. It's effortless to download these pre-trained transformer-based models from Hugging Face and use them. This is just one example. Now we have models, but they're still so big. What can we do? There's a technique called low-bit optimization. We know that the large language model generation latency depends on like at least three things: the memory input, output. It depends on the bandwidth. If it's fast and if the right input and output is fast or slow, and also the CPU, GPU computing, the flops. If the CPU is so good or GPU is so good, and then you have much higher computing flops, then you will have the latency much lower. And the thread synchronization. Then how do we tackle these things? This is one example to see, here's your chip. The CPU or CPU, you fetch the data from the memory, and then you do the computation in the chip, and then put the data back to the memory. Then in this whole process, we use like a CPU example. Currently, we use the FX instruction. Is pretty widely used for CPU. It can support like for example 512 bits calculation in one instruction. Then if you handle this data, for example, if your numbers is FP34 compared to your numbers in int 8, of course, if you handle the numbers in 8, it will be 4 times speed faster, right? Because every time you handle this much data, you do this much calculation. And this time you do the same amount of stuff, but you have more numbers calculated. So that's like a 4 times speed faster, right? Then that will be 4 times through more, like throughput. Does that make any sense? Okay. Then except this one, there are another actually for NVIDIA's chips, for all the A100 and a lot of other things, there's some like a int4 support or int8 support, but there's no native support of int4 tensor or layers in PyTorch or TensorFlow, currently at least. But at the meantime, there are too many third-party libraries, but they are not optimized on Intel platforms. And it takes a lot of effort to do the migration, because you have to collect a little here, a little there. And once we go into the chips to the very low level, it's pretty complex. It's a lot of complex than application for my including my experiences. So you have to collect a little bit here, a little bit from there, one instruction from here, another optimization from there. We want to put all them together. That will be a good example, right? That will be a very good solution if we put all this optimization together for Intel chips. Yeah, if we want to go a little bit details into the low bit optimization, here's I put a little bit of math here. We call like a model quantization. Generally, the goal is we can put larger models on smaller device, because we just put the model, we shrink the size, we put the same numbers of the same numbers of all this data, but more numbers. We put the same amount. For example, this much memory, we can hold more numbers if the size is much smaller. Then potentially we can get lower latency because of the, as we talked before, the I/O and the computation and so on and so forth. At the meantime, there's a lot of like int4, int8, NF, or GPTQ, all kinds of different formats how to quantize these models. Yeah. The benefit is so big. Think about this. If we compare to this guy, it's a Llama2 7B, the FP16, that's a generic one on Hugging Face right now. We would have 14 gigabytes, the model put into memory. But if we quantize into 4, that will give us 4 gigabytes. For the 70 billion parameters, we can downsize the size in memory from 140 gigabytes to just 40. So a lot of chips can handle this now. Yeah. So if we go a little bit into the details to say how to quantize the model, here's just one example. Think of this as a one vector. And if we use FP16 vector like this is one embedding of some word. Use the example. We get the max, then we can calculate the quantization factor according to the range of our format. Let's say this use int8 as example, the range would be minus 127 to 127. Then the quantization factor would be between this guy. Then that will get 23.5. Okay, so every number we multiply this quantization factor, we will get another vector we call the quantized vector. This is within the range of int8. Okay, does that make any sense to you guys? Okay, so we just do this one calculation and we put this vector into a smaller size. from FP16 to int8. It's just the half of the original one. So the same thing we can do int4, or sometimes we even tried int3 actually, but here just an example. If you might have this question, but at the end of the day, when we do the output, we still output we don't output the int8. We output the original. We want to output the original. We want FP16 or FP32. Then there's another one. We want to dequantize that. We just simply divide this number, then we get the original one. By this two calculation, like quantization and dequantization, we have this flipped and flopped. Yeah, but you might think there might be loss. Yes, there is some accuracy loss, but how much is that? Does that matter to our large language models? That's a real question we want to answer later. Okay, then after I have been talking about what large language model is and what our challenges are, and there are some techniques outside, for example, like quantization. Then we go to BigDL-LLM. We want to tell you guys, and I want to give you an overview how BigDL, large language model library, leverage all the open source stuff and the existing technologies to handle all the challenges that we have. Okay, here's BigDL, large language model library. BigDL start is an open source project start from 2006. Oh, I mean, yes, 2006. Open source led by our fellow Jess and I at the, 2016. I'm sorry. I'm so sorry. It's not 2006. It's 2016. It's 2016. From the very beginning, we focused on deep learning. We built a library like we wrote all the code in Python and Spark, Scala, leverage Spark, and we have just two languages supported, Python and Scala, to support all the deep learning libraries. We build each layer. We build all the optimizers and all the layers, all the also we construct some models there, and we also build end-to-end applications. We open source from 2016, and it was pretty popular by that time because a lot of people are using Spark, and on Spark we have this deep learning package, and a lot of people using it, and we're getting a lot of customers. From there, we start accumulating on AI applications. Now we are fast distributed secure AI because we put privacy there too. We have another package called PPML. That's a privacy preserving machine learning. So a lot of people care about privacy, and they just put it into our PPML framework. Then we'll guarantee that you can get the best technologies of Intel chips to guarantee your privacy. That's another one. The large language model library is recently developed by Intel. It's part of this project. It's a library that makes large language model runs fast on Intel XPUs. When we talk about XPUs, anybody has some clue on XPU? Okay, so it includes both CPUs and GPUs by Intel. And we develop this application from client to cloud, from CPU to GPUs. I will go through a little bit later. Because we are open source project, we leverage a lot of open source projects too. And we get it together and we follow the most standard open source project like Transformer APIs and other things. So we are very developer friendly. If you guys are just familiar with Transformer APIs or any other PyTorch standard models, it's very easy to get into it. So to do a little bit summarize what we support here. Before that, I want to say like XPU, you might I started from client to cloud, from CPU to GPU. That includes all the the young chips, the core chips, and the Flex, Arc, PVC. The PVC is our new GPU chips on cloud, and Arc. Flex is also, but it's a little lower end than PVC. Arc is the GPU on standalone machines there. Except this cross-platform support, we build a lot of support to help like transformer users and other like LangChain AI users to get familiar to use other models. So a lot of models, for example, if this model is popular, we can support it. Then once you find the supported model on our GitHub, on the examples under there, you will find that it has the lowest latency and the smallest memory footprint on Intel XPU. Then maybe a lot of models, some people like Llama, some people don't like Llama, they like other, like let's say Moss or maybe just GPT, then you can find it from our places. Except all this like a lower level support for some specific models like Llama or GPT-2. There are some other things we changed. We might optimize the model too. For example, for Llama, for the KV value cache, we just did some, we let the model cache a little bit more and then let the latency much lower. And the tokenizer also, we did some optimization too. So to summarize, we support a lot of models, almost all the popular models on Hugging Face there. And we guarantee you will get the lowest latency and the smallest memory footprint. Also support like features, in terms of compressions, it's like this is a different formats how to do it. And Llama CPP is the one that they write Llama in C++ language, and the GGMO is a format that they do. Like GPTQ is another format how to quantize a model based on bytes is a technology that we leverage to use into our stuff. Then also GGUF, AWQ, it's another different format. So we support all of this. Yeah. And in the optimization, some people may say, hey, maybe I can use int8 or FP8 because I have this much and I don't need a big model, but I need more. I can handle smaller model, but I need a little more than FP4, int4. You have a choice. So we support all this low bit optimizations from FP4 to int8. And it's cross Intel XPU. This is good for developers because like when we develop some code, for example, I usually do on my laptop and then I develop on the cloud. So you don't have to change that much. Then if you just develop your code on your laptop, you just push the code to the cloud, then you are ready to go. And that's it's pretty handy actually. No matter if you're using CPU or GPU, client or cloud, you can use our code to do it. Yeah. Then for any standard PyTorch model and API, then we support that. You just import from our library. Then you will use almost exactly the same code as you do for PyTorch. Yeah. And we also support like low bit fine tuning, like a CoLoRa, CoA-LoRa, and also continuous batching. Then with the development of the large language model outside, we support. Yeah, we just want to make sure all the applications, all the most recent and the people use applications can run on Intel chips with lowest latency and smallest memory footprint. Yeah, that's the goal. We want to make sure everybody can use it. Okay. To answer a question, to say, hey, because you do this calculation, you quantize the model and you dequantize some part at the end when at the output, but how much accuracy do you lose? The answer is very little accuracy we lose. Here's the example I show you guys. This is done by using harness evaluation framework. It's kind of standard outside. And each column here is a different tasks. Bool, Q, Pico, Pika, and HelloSwag and other things. So each column is different task. So let's do a comparison. If we just work on the first model, we compare the BF16 versus the int4. The accuracy drop just less than 0.1%. Is that good enough for you? I think the answer is really good. Then after we do this quantization, we don't lose that much accuracy. You may want to know why you, we did some example actually before. We did the int8 for next stable diffusion. The answer was not very good. After we quantized the model and it didn't go very well, the output image was not as good as expected. But for large language model, it's amazing. There might be a reason. Can anybody tell me why? Let me see, somebody. Okay, Iris, XE, I'll go back this later, yeah. The reason I think in this way, I interpret in this way, actually, it's pretty intuitive. Think about this. If I am predicting, I'm processing this one, I'm doing inference on this Llama model, my next prediction, my next word of the prediction would be cat, let's say. The probability, if we don't use a quantized model, the probability would be like 90%. But if we quantize the model, the probability might be 91 or 89% to have cat predicted. So does it matter to you? Actually, it doesn't matter, right? Because no matter what like a probability you get, as long as it's the largest, you still get cat. So that's why even sometimes you lose a little bit accuracy or precision in the data, but the precision at the end doesn't change that much. And that's why we can do this quantization. Yeah. And it does pretty well. Okay. Then, okay, that's what I want to cover for BigDL large language model library. You might want to know the performance. I can just tell a little bit, but because when we want to publish all these numbers, Intel is very, very careful. And I didn't put the slides there yet. But for this Llama 70B, at least we can get 20 milliseconds for next word. Yeah. But what I can show you guys, is okay, is the demo here. This is without BigDL quantization. This is with quantization with it's Chinese, but you can you don't have to understand the Chinese, but you just understand what's going on here. So it's a client put a question here and the large language model as a backend answers. So you can tell the right one is way faster, right? So that's the quantization helps. With the BigDL-LLM quantization on the PC, and it's much faster and give you this acceptable. But on the left side, people might, it's too slow and it has a very bad experience. Yeah. So we can summarize, we can make the conclusion that BigDL large language model library brings significant speed up. Okay. This is another example on Intel Core CPU. So even just Intel Core CPU, it does this pretty well. Yeah. Yes. Okay. This is another one. This is 4 cores. This is a 1 core at the same time. But there's some a synchronization. Yeah. Okay. So this is a 70 billion parameters Llama2. This is on one socket on the Intel Xeon SPR there. We can tell it's pretty acceptable, around if I remember correctly, I think around 30 or 20 milliseconds for the next word to generate. Yeah. Then that's our recording. Yeah, there's another one on GPU on Intel Arc. Slightly even more faster actually. Yes, this is about coding. Yeah. Any questions? Okay, so here, after we saw the videos and we saw what the BigDL-LLM can do, you may want to know how to do it. I will just show a very few code slips to let you guys say how to do it and how easy it is to, if you are familiar with like a transformer APIs or non-chain APIs. This is when we install it, we will have some requirements. Like at least you have a 12th generation core later, you want to have at least 16 gigabytes. I think nowadays everybody at least have 16 gigabytes memory. Just your laptop, you have more than that, right? Okay. Even Windows, we can do it. Or like Ubuntu, that's a Linux system. When we install it, just people install BigDL-LLM with all, then that will include all the other libraries too. So if we, let's say one example, if you want to run a PyTorch model to optimize the model, here, this is a Whisper API. You just import it, optimize the model, this API, then we load it, we optimize it, then we just call as the original like a transcribe, then you get it. So there's one line code add here. Model, we call optimize the model this way. We use here, we use like a low bit format as a symmetric int 4. Yeah, then you can do it. It's pretty simple and intuitive. For the standard like a transformer API, Hugging Face API, Hugging Face transformers APIs in here, instead of loading from transformer auto model for causal LM, you imported from BigDL-LLM transformers. Then that's it. It's even simpler actually. Everything else is the same. You just call model from here. Auto model for causal LM from pre-trained. Give your pass. Here you want to give it. If you give it a load in 4-bit as true, that will give you our default int format model. And that will give you a much slower, much like faster and with the lowest latency. If you don't give this number or you just load, you can load as original, that will call Hugging Face API. Yeah, but you can do a comparison. If you give this as true or false, you will see. You can also give like a format you want. Could be like a symmetric in 8, could be symmetric in 4 and other things. Then for other code, is exactly the same for the transformer. You do just from transformer, import the auto tokenizer, get the tokenizer, encode it into IDs, and then generate. After that, you decode it. You get the output. Yeah. So any one line of code change, just from here, from BigDL-LLM transformer import auto model for causal LM, then you will get the benefit of BigDL-LLM that has the most recent optimization. Yeah. Okay. It's pretty fast to scale to new models, and we have very easy migration of existing applications. The reason I want to say like it's very fast to scale because the technology for us is like we didn't write like as Llama CPP because they write the whole model in CPP C++ in a different way. For us, like we did it in a slick way. For once we know the model for the linear layer, because all this like large language model recently, the most of them are just linear layers. More than 90% of the layers are linear layers. We replace the linear layers from original one to the linear int 4. So all the weights are quantized into int 4 for the linear ones. That covers most of it. And we just replace that one. Then you don't have to like write every model in a different way. You just replace the linear layer, then you will get the benefit. Yeah, so that's what we say. We are very fast to scale to new models. This is another example. If you are just save and then load and save the model, you just save from pre-trained, you load it, and you just want to save in low bit. So this one will with the low bit, like int 4 optimization, not the original like BF16 anymore. Then you just save this one, and the tokenizer you can save it, but it's the same. You load it, you just call this load low bit, then you have the model already This is useful sometimes because when you download the model, you save with low bit, and then you next time you load it, it's much faster. Yeah. This is for non-chain API. It's similar. This is a code slip. Yeah. When you get this one, you load it, import it from like BigDL long-chain LLMs, import the BigDL-LLM. Then everything else is the same, but in here, you contact this model in this way. LLM equals BigDL LLM, then everything else is the same. Now you can just call run, then you will get the question answered. Yes. Okay. For this another, that's how we do the inference. You may want to solve the fine-tuning part. There's still some use case people use fine-tuning. Similar. You just load the model. Let's say load in low bit NF4. Then this is example on XPU. So you just put the model to XPU. That's you can use ARC and other things. Then everything is the same. The one code change is here. Load in low bit. That's highlighted. And you want to put the model to CPU, then everything else is the same. Yeah. I mean, of course, you want to load not from transformers. You just load from BigDL's transformers. Yes.
Guoqiong, should we answer the question, some user audience question first?
Okay. Are the optimized specific to Intel family of processors? Yes. The question is the optimization specific to Intel family processors? Yes. Can I use it on CPUs from other companies? No. It's for Intel chips. At the very beginning, we want to make this one for Intel chips. Yeah. Okay.
What about the first question, the Intel Iris Xe?
I just ignored that one. Is Intel Iris Xe a good processor for ML workload? To be honest, this one I have to check. And personally, this one I didn't do this work on this Iris Xe. Yeah, I will check and get back to you if you want to. I will send an email later to maybe Dr. Hu. Yeah.
Okay.
Yeah.
All right.
Okay. Yeah, that's yeah, it could be a problem sometimes, right? There are so many chips and we want to support. Okay. This is an example. This is another example of using CoA-LoRa. It's very similar. You just put here from CoA-LoRa, get the perf model, and when you load the model, you load in no bit. That's it. Everything else is the same. Here, I think I'm out of time already, but if you guys want, I can show you some tutorials there to see.
Yeah, we still have time. Go ahead. Yeah.
Okay, sure. I can show you how we do it. Yes. For example, if you want to build an application, because the BigDL-LLM is a library that you get the optimization and everything over there. But how about if you want to do some applications, you want to start with something, this is the tutorial that you can start with. Get some application done very soon. This first is an introduction, and it tells you how to set up an environment, and then give the application development basics. And this is training support. In here, I'll show you guys one thing. For like a chatbot one, just for example, how we do it, how we build a chatbot in here. Then this is how we install on CPU. You just first pip install, that's it. When we call like a pre, we get the pre-public, get the latest development. That's a good suggestion for a current development because it's going on very fast. Yes. Then we use this one as example. You just from Hugging Face Hub, you call the snap download. You can download the model, give your token, give the rep ID. You can download the model. After you get the model done, it's downloaded to Hugging Face home. Usually it's under cache if you don't change in there. Then it's our part. After you got the model, we want to load it in model in 4 bits. That's we test the most in 4-bit, and we got the most gain there, and that's our default one. We just make sure node in 4-bit as true, and we want to make sure you import this model not from transformers, but from BigDL-LLM transformers. Then you will get the model in 4-bit. Yes. Then after that, you just load the tokenizer as originally how you do it with any other Hugging Face models. This is a Llama one. You just call the token Llama model tokenizer from pre-train. You get it. You see one example. You see give the save directory, save the low bit, and then we save the tokenizer too. Then you can load it back if you want, or if you just example to show how to do it. Actually, it's you don't have to. Then we have this model in 4-bit and the tokenizer ready. Now we can run a model. We'll run this model in a chat application. Here's just example. Oh, you're beautiful. Some next respect Ollie's assistant, who always answer questions as helpful as possible while being safe, or something like this. Then just one example. Here, you give the system prompt. We define this format prompt. This is a Llama format, how we do it. Then in this chat, that's a thing. For whole thing, you want to put this one into history, and then send one as one response and get the model output. That's the answer for the whole thing there. Then we got the prompt, have to append the like a previous. Then that's when we define this how we format this prompt. Then there are many other things, like Dr. Who is very familiar with how to do this in a much better way. But this one just show you example how to do it. Yeah. Then we define this chat application methods. We got here. First we want to format our prompt, then tokenize it, encode it into IDs, and then call the model generate. We got the output IDs, and then we decode it. You got a response. Simple, right? Yes. Okay, that's how you do it actually. And so this is, you can just put it wrong like this. While true, you get this one with torch inference model mode, and then you just call chat. Then you can just chat and say, hey, what is CPU? Response, hello, I'm glad you asked. CPU stands for general processing unit, blah, blah. Or you can play with it for fun. As long as you have an Intel chip CPU and client, like anyone has a very, very cheap, like HP computer, laptop is so cheap, like just a couple of $100, and you can play with all this stuff. Yeah. Okay, then that's what I want to cover. But if you want to, this is another stream chat. It's a kind of, you give it as a stream. It's very, use this one as, use a streamer to handle. Then it's actually the same, the major part is the same. Put this one into thread, and then append the output, and then get back to the one, and format it, and then tokenize it, and then do the generate. That's it. Okay. So we can just go here. Probably I recommend you should need this one is a good start point. You just can play. You can develop your own natural language model. You can develop your own like a service. That's pretty cool. Yeah.
Can you talk a little about fine tuning now? Since this is prompt engineering, can we do fine tuning on this? Do you have example?
Let me see. Okay, so we have examples on fine tuning too. This is and if you guys if anybody knows how to do this one, it's fine tuning MB. Yeah, this is because fine tuning it's a little more resource, and it's a lot more slower on CPU. we use the GPU as example. This is when you put in storage, we want to make sure it's from XPU. And this is the IPEX, that's dependency for this is our library. And I want to make sure transformer is a little bit later, not the old ones. Then it depends on the path model and also accelerator. Just make sure everything is there. And the store set, make sure the one API environment is ready. So one API is kind of a library similar to CUDA. But this is on Intel chips. CUDA is on NVIDIA chips. Yes, just make sure the environment is ready and get sure we want to import IPEX. That's Intel extension for PyTorch. Then we call this node model in node partition. Here, node is in node bit as NF4. I think we tried a lot of other things. They just found out. I don't know why they put the NF4 there. Maybe the engineer really like this one. Then push the model to XPU, to GPU. It's not on CPU anymore, then it's on GPU. Then we get the data down. This is get the model prepared for this training. Yeah. And then put the configuration ready for LoRa. Then transfer model into a path. Yeah. Then that's a model prepared. After that, just load the data set. This is use hybrid English quotes. It's just example there. You can have your own data and then process the data into a tokenizer one. Then here, load the tokenizer. Just from pre-trained, give the path. That's it. Yes. Yeah, there's some padding. Yes, if you're the one you want to left side, you want to pad it, because the data won't be equal length, anything. Then everything else is the same as you run other trainer. Get the trainer down and put the training arguments. How many times you want to warm up? How many steps you want to predict? Yes. Then the learning rate and so on and so forth. Yes. Then you can just run the trainer as train. Yeah. Then that's it. The technology is done in the backend. Yeah, but the code just look like this one, very similar to Hugging Face. It's not similar, it's exactly the same. Yes.
So why does it require GPU to do the fine tuning?
Yes, it's training and fine tuning done in int4. Here it's in NF4 using this example, but you can use int4. Yes. So does the BigDL library quantize the model on the fly based on the parameter while loading? How about using models that are already quantized? That's a really good question. So when we load the model, we don't do it on the fly. At the beginning, we just load it, then quantize it, then put in the memory, delete the old ones. Then how about using the models that are already quantized? That depends on the quantization technologies and format. We support different types of quantization. We can load the different types of models too. Yes. If it's quantized, we can just load it. If the format we support. Okay. Okay, one message. Okay, yeah. So the goal for our team is we have 30 people, more than 30 people work on this. We want to make sure that big deal, large language, especially large language model part, is not some people's toy. It's generic for everybody. Everybody can use it. Even you just have a laptop within 16 gigabytes, you can run your own Llama. If you have a big cluster, you are ready to do the fine-tuning and other stuff. But at least if you have a laptop within around 16 gigabytes memory and 12th generation chips, you can run this inference. Yeah. And we want to make this familiar with developers as well as researchers. For example, I have friends working in universities or research labs. For them, they are not engineers. They don't have that domain knowledge actually to do all this stuff in that way, to do all the quantization, to collect all the permissions in the open source community. So if they are dependent on all this collection, like a BigDL-LLM, and it's very handy for all these researchers and developers, because once you develop your code on your laptop, you are ready to deploy as a cluster on other places, and you don't have to send all your you don't have to send your questions to OpenAI if you don't want. If you care about privacy, and you care about your employees' privacy, you care about the company's privacy, you probably just want to deploy your own model at local, you can start from BigDL-LLM. Yeah. How about the performance benchmarks of BigDL compared other local library tools? We compared one, and we have to say outright we claim that we have the lowest latency and the smallest memory footprint. And that's a valid comment. Yes, we did a comparison and we have a better one, and we are generic enough to support a lot of models. If we just know Llama CPP, you are bounded with Llama, that format, and you cannot use other models like Math or like GPT. You have to write your own C++ code to get the quantization done, or you want to leverage other open source packages to quantize the model in that way. So it's a lot of work. But if you use this BigDL-LLM, it's done in replacing the linear layers using a int4 linear layer, then it's done for you. Yes. So I want to, the thing that I really want you guys to get familiar with today is, that's a takeaway for today is, let's see, at the end. Okay, this is okay. Okay. So that's our library. Our library is for running large language models on your Intel XPUs with very low latency and a very small memory footprint. In this application, this library could be run across platforms, from client to cloud, from CPU to GPU, from ARC to PVC. And this BigDL-LLM optimizations are for any PyTorch models. And if you are familiar, I guess nowadays, if you're not familiar with PyTorch models, it's pretty hard for you to understand machine learning. But anybody who are familiar with PyTorch models, you can leverage BigDL-LLM optimizations. Yes. So if you guys want to know more information, visit our GitHub. If you guys want to do start some applications, go with our tutorials, then that's what I want to cover today. Yeah.
Thank you so much.
I'll take questions. Yes.
Yeah, now we are open up to questions. Anyone has a question for Guoqiong? If you have a question, you can unmute yourself.
Yes, I will take the chat too.
Yeah, my comment is very impressive, particularly when you compare after Inter4, the performance degrade is not that much. It's only like 0.1%. Some
less
at
than
most
0.1. Yes.
Yeah. So that part was very assuring. Because what we are afraid most is losing the precision, losing the accuracy.
Correct. I totally agree with you. So when I saw this one, when we did the evaluation at the very beginning, when we started the project, the very first thing we have done is to do the evaluation. We want to make sure if this technique really works, if the accuracy degrades so much, beyond what we can accept, what's the point to downsize the model? Because you will get a garbage, you get a junk. So nobody wants to do that. Then luckily, and the business stats, I think this is really awesome.
Does that depend on the library you implemented or any other people doing quantization? The Int4 would get the same result?
And if it's the same format, if the same technology to compress a model, I believe everybody will get the same results.
Okay.
Yeah, but Intel we just put everything together, good compression technologies, and get the optimization done on Intel chips to get the performance better. Yeah, because we are eager to sell AI chips. We want to make sure everybody can run large language model on our chips. Last day there was Pat was going to say for the AI PC and other stuff. And for other cloud, it's data center chips. It's under development. We are undergoing all this stuff to make sure it's happening. Yes, everything is developing very fast recently.
So right now, this BigDL-LLM mainly apply to laptop PC.
Yes, so I want to that's the reason at the very beginning I submitted the title in that way. I can run, or you can run, anybody can run a large language model 7B on your laptop. Yeah, you can just start from there and then go with the cloud. If anybody wants to try like a Intel GPU, just go to IDC, the Intel Developer Cloud. Then you will get we have our examples ready over there. You will go to the trailing and then you will see there. Yeah.
Okay.
So if this goes well, if anybody wants to know more, we can have a training session on how to run the inference and the fine tuning. And then we can collaborate with IDC to see if they can provide some like a resource to do the fine tuning and the inference there. Yeah. That depends on the interest. So here, at the beginning, I just want to introduce what we are doing and how good it is. If anybody wants to get a little more, we can host other sessions too. I'm okay to do that. Yeah.
Yeah, this is very good, and I'm actually going to spend some time over the next couple of days in actually deploying a Llama version on my laptop. Hopefully, it's easy enough with your Git repo. We'll try it out. I can give you some feedback on how well it goes, or if I run into problems, I can maybe contact you or whoever experts kind of can help us out. So that's really good. Thank you so much.
Thank you.
Yeah, we'll try it out. One question is, typically these workloads don't run on the laptop, right? Like for all my customers, for my company, we are deploying Llama models and we are optimizing those. There is a need to make sure that all of those models run like portably across different environments, right? So if I'm going to a cloud, in that case, if I want to use BigDL, am I going to need to provision some kind of a bare metal server? Because I don't know exactly what CPU, GPUs I might always get on a cloud. So how do you recommend we go about using this in a cloud environment?
Okay, so it's very similar to this question here. I will answer together in the same way. Does Intel have a cloud where one can try BigDL on the instance that does require a laptop with the Core 12? Yes, that's an Intel Developer Cloud. You can go there and try. You can choose like CPU or GPU or SPR or ARC or PVC from there. The short answer is IDC. The long answer is yes. You can just try there. And go back to your question, because you are not very familiar with the difference between CPU or GPU or any PU. It's okay. So my suggestion is you start from a Intel laptop, then that's CPU. Then you will start from there, and then that's one. Yeah. If you want to know more, because CPU you will get this like a slower, but on GPU you get much faster, but you pay a little more. So if you want to try GPU, go to IDC Cloud. And the starting point is always your laptop, if you have one. It's actually so cheap for laptops, actually. Yeah.
Yeah, so sorry, I was probably not clear, but if I were to use any of the standard public clouds and I want to use BigDL, what's your recommendation? How do we
You can do it. You can. They have like SPRs. They have a lot other. They even have Gaudi. I remember. Yeah, you can try from there. You can start from the maybe SPR CPU. Yes. Always good start point is from CPU because you always can do it because the CPU has, we can say nowadays, we can a lot of memory, way more than GPUs.
Yeah. You know, I deployed a 7B Llama on my laptop and it was a dog. It was so slow. It was pretty useless. So I'm excited about how this works. And I've tried the GGML, a couple of quantized versions. They were better, but not really working. So I hope the int 4 versions on my laptop work much faster.
Try it. Yes. Okay.
All right. Any other question?
What's the best way to get any kind of help or support if we run into issues with
the
this?
best way is to put the issues in our GitHub. When you run into some issue, for example, if you start from your laptop and you are trying the tutorials, but it didn't work for some reason, you just put the issue and somebody will contact you.
Awesome. Thank you.
Yeah, because that's an open source project. When you put something there, we will look directly right away. If you even sometimes you send the emails, they might not remember. But the GitHub on there, everybody, our fellow is working on that. So I have a question for you guys. Anybody interested in another session of tutorials to run it with me?
Yes.
It depends on how many.
Yeah, I have a hard stop in another 15 minutes. How long do you think it will take?
How long does it take it to get what? To get a resource? I mean,
to get everything up and running as a quick tutorial?
it's 5 minutes.
Oh, let's do it.
Not today, because not today. To get it run and get it, but prepare everything. I want to prepare that one better. I want to get the model download to my one. Yes.
Awesome. No, that would be good. We could absolutely would love to have you back and maybe for a shorter session, and journaling could absolutely help us get that session set up.
We'll see. Because if we just start next one, somebody might run into the problem of like a Hugging Face or Transformer to download the code, to download the model, to download the tokenizer, anything like that. That will take a long time. But if we want to really start some like a training access, I want to prepare the notebook in a better way, in a different way. Yeah.
Okay. Well, we will see. I think once people get familiar with the library, maybe they will have questions.
Exactly. Just start from the library and from the tutorial, and then let's do a more.
Yeah.
It's too much if we want to cover both the technologies of BigDL-LLM and the tutorial together today. It's kind of a lot, then I cannot focus on either one. So that's why.
Yeah. Sure.
All right. Okay. All right. So yeah, so thanks for sharing this very new technology. Most of us have not heard about it. So it's very even though it's not new for Intel, but most people we have not heard about how large language model can run on a laptop. So
Yes.
which definitely this talk is very timely. And I think without other questions, we can end here early, unless anyone else has a question. Okay, all right. So Guoqiong, thank you very much. Well, I will share your recording and put up on the YouTube for our audience, and more people will hear your talk from
Thank
today.
you very much, Dr. Hu.
You're very welcome.
Okay.
And thanks everyone for attending today. And we will. So this is our last session for this year, 2023. Next year we will start on January 5, and I think there will be more exciting development next year. And we look forward to a whole new year.
Then happy holiday.
Yeah, happy holiday, everyone.
Okay. Bye.
Okay, bye. Bye.
Thank you. Bye.
Thank you.